So I said previously that the strength of Parsifal's function, or Parsifal's theorem in Fourier transform theory, was that it allowed us to define an energy spectrum. And the energy spectrum allowed us to talk about the distribution of energy among different frequencies. And this brings us to our next discussion, which is about bandwidth. Bandwidth is an extremely important characteristic that we use to describe both systems and signals. And so what is the bandwidth of a signal? What is the bandwidth of a channel? These are concepts very important, but bandwidth is not necessarily uniquely defined. And so what we're going to cover now are a number of definitions that you will see when you are working with systems. And if you're purchasing equipment, it will be in the spec sheet for the equipment. It'll discuss what the bandwidth is. And from one spec sheet to another, it's possible that the definition of bandwidth could change. And it might be because for different kinds of systems, different definitions are more appropriate or more useful. And so we take the time now to go through different definitions of bandwidth. So this information is covered in section 1.7 of our textbook from Scholar. So first let's talk about band limited, and I'm going to talk about signals. And this is just a definition. So I ran through it briefly in the definition of linear systems, but now let's take a little bit more time to think about it. So what we have here is two examples. And if we look here in the column, I'm always looking at the time domain. And if I look here in this column, I'm always talking about the frequency domain. Column 1, time domain, column 2, frequency domain. But now I have rows, and in the rows, there are different examples. So let's start with the first row. In the first row here, I have something that looks a lot like a sinc function. In fact, it's a square of a sinc function. And a sinc function, what is its characteristics? This is in the time domain again. And a sinc function in the time domain, it has infinite support. From minus infinity of time to plus infinity of time, it has content for all this, this interval of time. Now, if I take the Fourier transform of a squared sinc, I know that the Fourier transform is a triangle. So if I look in the frequency domain, I have a triangular form, which means that after a certain maximum frequency, there is no frequency content. The frequency content is 0 after that maximal frequency. When this happens, I talk about a band-limited signal. So if I look here, this here is bandwidth limited. Now, suppose I want to look at a counterexample. What is an example that is not bandwidth limited? Well, I'm just going to do a real slick trick here. I'm just going to swap the time domain and frequency domain. I know that if I have a triangle in the time domain, then in the frequency domain, I'm going to have a sinc squared. Okay, so now I say I have a triangular function in the time domain, and in the frequency domain, of course, now I have a sinc squared, which has infinite support, which means there's content in almost all frequencies. Of course, it passes for 0 a few times, but still it does not equal 0 at any point. Of course, it decays, and so for practical point of view, you could think of it as band limited, but that brings us to our idea of what is the definition of bandwidth. Here, the bandwidth of the signal, very easy, because after that, it's band limited. So the bandwidth content is very clear. Here, it's less clear. I could say it's infinite, but practically I know it's getting smaller. So at some point, you know, it's negligible. So how do I define that point where it's negligible? And that's why we have multiple definitions of bandwidth. And I'll just step back and say that this, we might give a notation or vocabulary to, and say that this is a time-limited signal. So this signal, it's only non-zero for a specific interval of time. All other time, it's 0. So this idea of bandwidth limited and time limited, we can sort of start asking about what is realistic. Well, time limited seems real realistic to me. I don't have you know, when I go to the lab, I go on Tuesday, I start my signal then. It doesn't go to minus infinity. So time-limited signals seem realistic. But what about when I look at those spec sheets on the equipment I'm using, and this equipment, they have limited bandwidth. If my signal has infinite bandwidth, has frequency content for all frequencies, when I go and I buy equipment with the electric circuits in it, the circuits, well, they have sort of finite bandwidth. So there's this problem about infinite bandwidth signals and band limited maybe channels. So these are the ideas that we're trying to grapple with as we define the bandwidth of a signal or the bandwidth of a system. So a time-limited signal cannot be band limited. So the two examples I gave were, one specific one. It was a triangle and sinc squared. But it can be generalized. It can be generalized, and if I have a time-limited signal, it can't be band limited. So if one is limited, then the other one is not. This just comes right from Fourier theory. We do have this idea of roll-off, that asymptotically they're heading for zero. And so if we were going to think about this idea of it may not be band limited, it might not be at a specific frequency that is exactly zero, but there is some point where it becomes negligible. And it depends on how quickly it rolls off. So roll-off might be an important concept when I'm thinking about signals and channels. So this all brings us to this question, as I mentioned, is how do we quantify bandwidth? So how do we quantify it? And again, why is it important? How am I going to exploit these definitions of bandwidth once I have them? Or how am I going to use it? So let's look at some simple examples of paired off signals and channels. Okay, signals and the systems that these signals pass through. I often call the systems channels, because in communications that's how we think of it. So in this case, I have rows and columns again, but in this case everything's in the frequency domain. And I have, in the first column, I have my signals. What do I put into my system? And in the second column, I have my system. What am I pushing them through? And of course I know that because these are linear systems, I know that y of omega is just equal to h of omega times x of omega. It's a linear system, I know that. So if I wonder what's going to happen at the output, well, it's going to be the product of these two things. And now I have two examples. And the two examples, these are the rows, the first example, most of the energy in the signal is concentrated near the origin. And in this system I'm passing it through, this system is pretty wide. The area where there's no distortion introduced is pretty large. Second example, in the second row, I have a signal which has content, a lot of energy even in high frequencies. It's not as concentrated in lower frequencies as this first example. And in my system is very narrow band. My system is not allowing a lot of high frequencies to go through. So what's going to happen at the output? So if I think of the multiplication of these two, well, when the channel response or the frequency response is pretty flat and equal to 1, I'm going to see most of the energy in my signal. So intuitively, I know that at the output here, the y is going to look pretty much like the x. It's not going to be changed much. So imagine this is a communication signal. I'm sending information through a channel, and I want that information to get to me. I don't want it to be distorted or changed. So this is the situation I'm kind of looking for. But I have to be able to identify, well, what happened if I'm in this situation? In this situation, I have energy all over the place. I have a narrow band channel. And when I look at the product of these two, well, I'm going to cut off a significant amount of the energy from this signal. And so it's going to be highly distorted when I look at it. If it's a communication system, I'm going to lose a lot of information about the data which was transmitted. So filtering effects and bandwidth, these are very important in communication systems. And so if we want to say, is my channel wide enough to accommodate the signal that I'd like to pass through it, well, I have to be able to identify what is the bandwidth of the signal and what is the bandwidth of my channel, and to try and keep them as close to one another as possible. So I'm going to be giving you several definitions of bandwidth. This is summarized here. We're going to start with absolute bandwidth, easiest to define. The 3 dB bandwidth, also known as the half power bandwidth, which is probably the most common definition of bandwidth you're going to find in your spec sheets. Noise equivalent bandwidth, very important in analysis of the noise effects in a system, so very important. Null to null, very easy definition. Fractional power, power spectral density bound. We'll be talking about each one of these in turn. So I say the absolute bandwidth is the easiest. Suppose I have a signal which is bandwidth limited, which means that this signal is 0 after a certain maximal frequency. So here is the m of omega, in this case, represents the frequency response of the signal or the system. And we can define the bandwidth as being B or 2B. So I just mentioned this because sometimes we have the two-sided bandwidth, which would be 2 times B, and sometimes they'll talk about the one-sided bandwidth. Now, I guess I'll take a minute or two just to, what is this one-sided versus two-sided? Why does it exist? We'll always be looking at the two-sided bandwidth. Do negative frequencies exist? No, they don't exist. They're a mathematical construct that is really simple for us to manipulate and predict what happens. So you would think that one-sided bandwidth was the one that we would worry about. However, we will talk about later about systems which are modulated, which are put on carriers, which means that if I use my Fourier analysis and it said that if I had a signal that looked like this and then I modulated it onto a carrier, it would actually look like this, where this was the frequency of my carrier. So now, when I look at this signal, it seems to be twice as wide when I put it on a carrier as it looked like when I was looking at it in baseband or at DC. Here's a DC, no carrier. And if I looked at only the real frequencies, B would be the bandwidth. But if I put it on a carrier, then now I'm seeing both sides. That's what's great about Fourier analysis. It predicts this, and this is actually what happens. This is what we observe. And so now the bandwidth seems twice as large. So because, passband systems with carriers are very common, we typically tend to talk about two-sided. But sometimes it gets ambiguous, sometimes it's important to understand the difference, and then we'll specify, be very clear, this is the two-sided bandwidth, or this is the one-sided bandwidth. So be careful on which definition you see. I said we use two-sided, but that's not necessarily true. I misspoke. We can either be one-sided or two-sided. And for instance, if we just say the maximum frequency, well, that seems a little less ambiguous, the maximum frequency, and we can use that for bandwidth also. So when I say B now, the B is the bandwidth that we'll be using, which is kind of the one-sided bandwidth. So let's look at 3 dB bandwidth definition. So this is the bandwidth when the spectrum reaches half of its maximum value. And typically the maximum value occurs at DC. So for instance, here we have a sinc function again, and it has a maximum value at DC of A, and it rolls off at some speed of roll off, and at a certain point it gets to half its magnitude. And when it gets to half its magnitude, that's the point we said whatever bandwidth I'm at when that occurs, I'm going to call that the bandwidth. Because 3 dB is the equivalent of when 3 dB is the measurement of having reached half the value, that's why we call it 3 dB bandwidth. Or full width half maximum is another way that we might call this bandwidth. Noise equivalent bandwidth. We'll talk about additive white Gaussian noise very shortly. And when I get back to talking about additive white Gaussian noise, I might then explain why we call this noise. For now, I'm not going to explain why it's called noise. I'm just going to give you the definition of what a noise equivalent bandwidth is. So I start with an arbitrary shape, and I'm going to keep with my example here, which is a sinc function, or the absolute value of a sinc function, as my spectrum. And in this case, again, I'm going to assume it has some maximum amplitude I call A. And in this example, of course, it has infinite support. But I can calculate the area under the curve. So this is a square integrable function. And because it's an energy function, because it's a practical function. So I'm going to look for the area under the curve. And this area, I'm going to say, I'm going to take that same area and I'm going to put it in a box. I'm going to put it in a box, and this box is going to have exactly the same maximum value as this one. So I take whatever the maximum value of as A, that's the height of this box, and the area of this box, I'm going to fill it with exactly the same area as this. And whatever, I have to keep making it wider or narrower so that the area gets right, and whatever size that is, that will be my definition of what the bandwidth is. So if I took all of the energy and I put it into a square box with this height, how wide would that box be? That's my bandwidth. So the next definition is the null-to-null bandwidth. It's nice because it's simple, easy to see, not much calculation. Where is it at half? Very simple. Where does it go through 0 the first time? And that's the definition of B. So we call this the main lobe also would be another name. So it's the main lobe bandwidth. Next definition is a practical definition. It's like, how much is the power concentrated into a certain area? For instance, if I take again this idea of area under the curve, instead of taking the area under the entire curve, I'm going to stop it at various points. I'm going to stop it at various points and look at what the area is, and I'm going to compare that area under a certain interval. I'm going to compare it to the area under the entire curve. So here in the denominator is all of the energy or the power. We'll see that some signals are power signals, some are energy signals. So I got a little loose here in my use of energy and power, but whichever one is appropriate, I'm going to take the ratio and I'm going to say how much is it concentrated in a certain band. And each one of those possible values for the percentage is another definition of bandwidth. Like the 90% bandwidth would be whatever this B is that gives me 0.9 when I take the ratio of the area under the curve for that value divided by the area under the curve of the entire curve. So that would be called fractional power, fractional energy, is another definition of bandwidth. So this is less dependent on the roll-off and more determined by the total area under the curve. I said 3 dB bandwidth was one definition, but it doesn't have to be 3 dB. Suppose I want it to be 6 dB or I want it to be 10 dB. And this could be, for various reasons, more appropriate. It might be more interesting to me to know what happens at 6 dB down than it does at 3 dB down, depending on the system I happen to be working with. And so we can just let K be any number of dB, and we will just look at when I start from the maximum amplitude until I get down to a value which is that many dB down from the maximum value. So finally, in the textbook, SCLAR, we have an example of a sinc squared. So here is the spectral density, is a sinc squared, and marks off in this graph. If I use the definitions that I've talked about, first of all, there is no absolute bandwidth because this is infinite support, so that definition doesn't exist. But we can do the half power. So if I look at half power, I get a bandwidth which is this wide. If I look at the noise equivalent bandwidth, I make that calculation, and it ends up being this B to B point I see here. So you see the box that's written. If I had a box that was the same height, that's how wide it would be. Null to null, of course I can see the null here. And if I wanted to get 99% power, of course I just go to MATLAB and start doing integrals until I found a width that gave me about 99%. And in this case that would be the marks here and here. That would be the bandwidth at 90%. Suppose I looked at 35 or 50 dB down for my definition of bandwidth. Well, let's take, for example, 35. And in this case, we're looking for, we put a line here, and of course it goes down to 35 here, but then it comes back up. So it's not the first time it crosses this line, but the last time it crosses that line. That determines that bandwidth. So the takeaway from this plot is that each one of these definitions of bandwidth gives a different number. So which number is the right number? Well, there is no right number. There's just different definitions. And depending on your system, one of the definitions may be more useful to you. So it's just important that I think early on we know this about when you're going to be reading spec sheets or when you're going to be working with systems, that there are different definitions and that you should make sure that you understand which definition you're using and that it is indeed the most appropriate for the situation.